What if the next meaningful step in AI is not making models bigger, but making them small enough to actually live where people use them? That is the pitch behind one-bit language models, and more specifically behind a new model called Bonsai 8B from PrismML. On paper, it sounds almost too neat. An 8 billion parameter model that the company says shrinks down to about 1.15 gigabytes, runs on consumer devices, and still stays competitive with normal 8B models. The important question is not whether that sounds impressive. It does. The real question is whether this is a genuine turning point, a smart marketing package around a research trend that was already underway, or a little of both.
To answer that, it helps to start with the basic idea.
A normal language model usually stores its weights in formats like 16-bit floating point. A 1-bit or 1.58-bit model pushes that to an extreme. Instead of letting each weight carry a lot of numeric detail, you collapse it into a tiny set of possibilities. In the BitNet research line from Microsoft, that often means ternary weights, -1, 0, or +1. The promise is simple. If the model can still do useful work with dramatically simpler weights, you cut memory use, reduce data movement, and potentially lower energy and latency too. That matters because a lot of modern AI is bottlenecked not just by raw math, but by the sheer cost of hauling huge weight matrices around. There is a subtle but important distinction here. A lot of local AI today already uses quantization. People run 8-bit and especially 4-bit versions of models all the time. That is normal. Methods like LLM.int8, GPTQ, AWQ, and QLORA helped make local inference and cheaper fine-tuning practical well before 1-bit models became a headline. So when people hear 1-bit and think, wait, isn't this just another compressed model? The answer is partly yes, but not exactly. The stronger 1-bit claims come from native low-bit model design and training, not just squeezing a finished full-precision model after the fact. That difference is why researchers got excited and also why adoption is harder.
That brings us to why this matters at all.
The cloud story has dominated AI because it works. Bigger models, bigger clusters, bigger bills. But many of the most practical uses for AI do not happen in giant data centers. They happen on laptops, phones, edge devices, factory equipment, robotics systems, and in privacy-sensitive enterprise settings where sending everything to a remote model is either too slow, too expensive, or just not acceptable. That is why so much of the market has shifted toward efficient local models. You can see it in the research around on-device quantization, and you can also see it in official small model releases from teams like Qwen, which are explicitly optimized for deployability and efficiency rather than just parameter count.
So where does Bonsai 8B fit? Bonsai 8B matters because it takes the 1-bit conversation out of papers and puts it into a commercial product story.
PrismML says Bonsai 8B is an end-to-end 1-bit model across the whole network with no higher precision escape hatches in the embeddings, attention layers, MLPs, or language model head. The company released it under Apache 2.0, built runtimes around llama.cpp and MLX, and framed the model not as a lab curiosity, but as something for real local deployment. In other words, the pitch is not just, look at our clever compression. The pitch is, this is a usable model family for devices people already own. That is the directional shift worth paying attention to.
Now for the part that needs more discipline.
What has actually been proven? PrismML reports that Bonsai 8B uses about 1.15 gigabytes for parameters in its GGUF release, compared with about 16.38 gigabytes for an FP16 model of the same class. It reports benchmark averages that stay in the conversation with full precision 8B peers, along with roughly 131 tokens per second on an M4 Pro Mac, 368 tokens per second on an RTX 4090, and around 44 tokens per second on an iPhone 17 Pro Max. Those are impressive numbers. They are also mostly vendor-reported numbers. That does not make them false. It does mean they should be treated as claims from the model maker, not as independently settled facts. There is another nuance that matters if you want to explain this honestly. When PrismML says 1 bit, the shipped format is not magic dust where every deployed parameter is literally one physical bit with no overhead. The Hugging Face card describes a sign-only weight plus shared FP16 scale factors across groups of weights, which works out to an effective 1.125 bits per weight in that format. That still represents a major compression win. It just means the phrase 1 bit is best understood as a model class and operating idea, not as an invitation to do cute arithmetic and ignore packaging details. And one more caveat. The 1.15 gigabyte headline is weight memory, not the entire lived experience of running the model. Real deployments still need context windows, KV cache, runtime overhead, and hardware-specific kernels. So yes, the small weight footprint changes what devices become possible. No, it does not mean every device with barely more than a gigabyte of free memory instantly becomes a perfect 8B AI machine. This is where Bonsai becomes interesting in a more serious way. Even PrismML's own materials say a lot of the current gains come from reduced memory footprint on today's hardware, not from some futuristic custom 1-bit chip. That is actually a strength in the near term. It means the model is trying to squeeze value out of existing Macs, phones, CPUs, and GPUs. But it also sets a limit on how grand the claim should be today. The strongest argument for Bonsai is not "the old rules are dead." It is, we may be seeing a credible new point on the quality-to-size curve. If that sounds familiar, it should. Microsoft Research's BitNet work already made the underlying case that native low-bit LLMs can be real models, not just broken miniatures. The 2024 and 2025 BitNet papers argued that 1.58-bit systems can remain competitive at the same scale while improving memory, energy, and latency. The BitNet.cpp work then tried to show those gains can translate into actual inference systems with reported CPU speedups and energy reductions. So the most grounded way to describe Bonsai is not as a miracle from nowhere. It is as a commercial extension of a trend that had already earned serious research credibility. That also helps answer the question of how important Bonsai really is. Technically, Bonsai is important if its claims hold up under wider testing, because an 8B class open model that stays useful at this footprint would be a meaningful deployment milestone. Commercially, it is important because it gives buyers, developers, and investors a cleaner story about local AI economics. Lower memory, lower energy, faster response, more private deployment. Directionally, this may be the biggest point of all. Bonsai suggests the race is no longer only about raw benchmark supremacy. It is also about how much usable intelligence you can pack into a constrained device budget. That is a different design target, and it aligns with where the market has been heading. But I would not overstate the production readiness of the entire 1-bit category.
Today, the mainstream local model ecosystem still leans much more heavily on 4-bit and 8-bit methods, because they are easier to apply to existing models and the tooling is much more mature. Native 1-bit systems ask more of the stack. You want the right kernels, you want model-specific support, you want benchmarks that are not just cherry-picked for the release post, and ideally, you want more third-party testing. That is why the most honest framing is that 1-bit is promising, but still narrow. The destination may be big, the road is not finished.
So what can people realistically do with this today?
The obvious use cases are local assistance, private document workflows, offline or weak connectivity environments, edge prototypes, and educational tinkering. If you want to learn what efficient AI really feels like on everyday hardware, Bonsai is interesting. If you want to prototype a privacy-sensitive assistant that runs close to the user, Bonsai is interesting. If you are shipping a production system tomorrow and you want the safest, best supported low-bit path, you will probably still look first at the broader 4-bit ecosystem and the stronger tooling around it. In other words, Bonsai looks more like an advanced early option than a universal default.
Where does the field go next?
Probably in 3 directions at once. First, better evidence. More independent benchmarks, more hardware comparisons, more real workload testing. Second, better software. More mature runtimes and easier support in standard tooling, so native low-bit models do not feel like special projects. Third, eventually, better hardware. If 1-bit inference keeps proving itself, vendors will have a stronger reason to design around it instead of treating it as a weird edge case. That last part is still speculative, but it is not random speculation. It is one of the main reasons researchers have kept pushing on this line.
The cleanest way to leave this is probably the simplest. Bonsai 8b does not prove that 1-bit models have already won. It does prove that the idea has moved beyond a niche paper conversation. The important shift is not that one startup found a clever compression trick. It is that the industry is getting more serious about intelligence per watt, per gigabyte, and per device. If the last phase of AI was about scaling up at any cost, the next phase may be about scaling down without losing the plot. And if that happens, Bonsai 8b may end up mattering less as the final answer, and more as one of the first convincing signals that the question itself has changed.